Hello everyone, this is Musimenta Tendo Divine from Group SWAI 9, and I'm here to talk about our AI project known as the Knowledge Graph-Based Spatial Temporal Intelligence for Real-Time Campus Crowd Detection and Recommendation. And this project has the following keywords, as you can see there on that slide, and below are the people, part of my group members. And then when you go to the next slide talks about the contents of the presentation. You're going to talk about the introduction, the related works, the problem statements, the research questions, and so on and so forth in depth, as you're going to see. So the introduction here talks about the problem, our solution, and the key technologies involved in this project. So our problem is basically crowding at some service points in our campus locations, such as the service points can be cafeterias, libraries, and maybe examination halls and restaurants, which may harm students' experience and efficiency and also safety. Then our solution is a real-time system to predict and manage these crowds using spatial temporal intelligence. And to dive into the key technologies, we have campus crowd management. The goal of this is to optimize campus flow and resource usage. And then we have spatial temporal modeling. This is understanding how crowds move through space and time. Space is basically locations, like through the different locations at different times. Then we have knowledge graphs. These are basically the smart maps that connect these different locations with context like events, class schedules, let's say examination times. And then we have the graph neural networks. The graph neural networks, this is basically the brain of AI that learns from the KGs, the knowledge graphs, to predict the future crowd levels. Then the fairness aware recommenders, this is an engine that suggests alternatives without creating new bottlenecks. It does equitability for the crowds. Then we have the privacy preserving analytics. This analyzes crowds ethically and also helps in anonymizing like geolocation data. Then to continue, we are going for the related works. The related works, these are basically the papers we picked out that talk about how to manage crowds, how to count crowds. And the first paper we have here is crowd forecasting based on Wi-Fi sensors, and it uses the long short-term memory networks, those are the LCTM models, and it was able to achieve high accuracy in forecasting crowd counts through these sensors. And the model limitations was that the model was processing data as independent time series, and it failed to capture the spatial relationships between the locations. Then the contextual limitations, it was limited to predictions only, it never offered recommendations. And then there is the 2020 paper of crowd counting. As you will see, this one was using foundation neural networks, and it was successfully able to estimate the crowd density heat maps from camera feeds. So this basically used camera feeds, and that was the context limitation it had, because you find that around campus it's not that every place has cameras and stuff. So then there is the TGCN, the temporal graph convolutional neural network for traffic predictions. This one used graph convolution networks and gated recurrent units. It effectively predicted the speed on the roads for the cars. And then we have its architectural limitations, the contextual limitations. And then to continue the next slides, there is another paper of 2018, another one of 2022. Then as you can see, the models involved and the limitations plus the rest. Then our project here, its contribution for it is going to be using knowledge graphs, temporal graph neural networks, and fairness constraint recommendation. And our aim here is to provide predictive density forecasts and fair context-aware recommendations for an entire campus. And this integrates a multi-relational knowledge graph to fuse the diverse data sources such as GPS locations, Wi-Fi data, schedules, and overcoming the limitations of the simpler graph or grid models. And the contextual limitation, we could say that it's explicitly designed for campus context only. Then we continue to the problem statements. We have the domain problems and the computational problems. So the domain problems these are basically real world challenges that we can face through this project. For example, inefficient resource allocation. Realize that university administrators don't have enough real-time data needed for dynamic resource allocation and maybe removing some services in different areas. So we also have degraded students experience, like this kind of setting, crowds, long queues kind of reduces the experience of students around campus, like it dreads their lives. So we also have the other one, reactive versus proactive management. So you find that in universities, crowd management is more of reactive, like they respond to these crowds after they have already occurred. Then when we go to the computational problems, these are basically technical challenges whereby the data we are going to use is heterogeneous, it's different. We have Wi-Fi data, GPS that are normally noisy, we have sensor data which is normally incomplete, and irregular, non-uniform time data, and we also have complex unstated relationships. So you find that some crowd behaviors are really complex and they have unstated relationships. For example, a student from a specific lecture hall going to a nearby cafeteria afterwards, that may be really unstated, because like if you didn't model it in your system, you may not be able to know. So moving on to our research questions and objectives. The research questions were basically how we can be able to model this complex environment, how we can be able to accurately predict these crowds and generate also fair recommendations, how can our system work in real time while ensuring privacy. And our research objectives are to develop a comprehensive campus knowledge graph that models these different facilities, pathways, and events and other contextual factors, to design and implement a temporal graph neural network model that performs crowd density forecasting, to create a fairness-aware recommendation algorithm that suggests the routes and service points to balance crowd distribution, and to integrate privacy preserving analytics in our data collection. Then moving on to our research contribution and outputs, we are able to develop an architecture that combines knowledge graphs and graph neural networks for contextual crowd modeling. And we built an innovative recommendation engine designed specifically to balance crowds in physical places with fairness-aware constraints. And we developed an end-to-end design that is practical, scalable, and built on a foundation of user privacy. We're able to create we are creating a valuable anonymized campus mobility dataset and a new class of analytics to empower data-driven university administration. Then moving on to our methodology of and system architecture. As you can see, number one is the data we are going to be able to collect and use, which is the mobile geolocations, Wi-Fi access logs, IoT campus sensors, scheduled events, and then this data is going to be fed into the knowledge graph construction, where we construct a knowledge graph based on this data, and we'll be able to find out the facilities, pathways, the edges, like the relationships between there, and also being able to anonymize some of this data like mobile geolocations. And also this knowledge graph is going to feed into the temporal graph neural network model to smoothen these noisy traces and also latency, and be able to forecast densities, then through the fairness-aware recommendation to be able to balance the crowds. And these are going to be received through phones and also to administrations and to students or laptops. Then we move on to our model architectures and mathematical foundations. You find that this first model we are going to look at, that's its architecture. And so diving into the mathematical foundations for the spatial temporal graph convolution network, which is basically our primary model in this architecture. It inputs time series data mapped to graph nodes, which are facilities or locations, and it has the different layers, the temporal convolution layer, which basically works on the time dependencies, then the graph convolution layer, which captures the spatial dependencies, then the output layer, which predicts the crowd levels. Then those are the mathematical foundations, and how it works. It learns from how crowds evolve over time and how locations influence each other. The limitation, it's sensitive to class imbalances, and in a way we had to solve this is by doing oversampling on our data set to prevent the model from getting biases from the minor classes. Then we have the graph neural network for knowledge graph reasoning, and this basically models the spatial dependencies. Its input was the knowledge graph, and the different layers involved are the graph convolution layers. This basically capture the spatial dependencies, as I've said previously, then aggregation, then the output layer that gives the recommendations or classifications, like it's crowded, this place is not crowded. So these work in hand in hand to be able to give you a fair recommendation of the density of the crowd. Those are the mathematical foundations. So this aggregates the information from neighboring nodes to infer crowd patterns and make recommendations. Its limitations is over smoothing, and how we were able to solve this is carefully. We did a careful layer depth selection and explainability audits. So continuing to the next model that we chose, where this model combines the TCN, temporal convolution network, to capture the time-based crowd patterns with the graph convolution network that leverages facility relationships from the knowledge graph, and for crowd predictions and fair facility recommendations. Then these are the mathematical formulas. Each filter learns from short time and period temporal dependencies. As you can see, we have a fairness ranking. So moving on to our third selected model that we use to train and see how it works. This is a model, an assembled model with a relational graph convolution network model, RGCN, that is responsible for capturing the relationships between facilities based on their static semantic relationships. Then we also have the graph attention network, the GATT, that captures the spatial dependencies by learning attention weights between the neighboring nodes. And then we have the temporal convolution network, responsible for temporal evolution of crowd behaviors at each facility. Then the hybrid model basically combines all of these models to be able to give a fair recommendation, as you see. Then we move on to our data set. The data set had 10 columns and 207,315 rows, and the objective is to fundamentally understand the data set, its structure, its size, and we found out that it had 68,162 empty rows in acceleration. We're able to see our data types. The first, we had floats, we had objects, we had ints. So basically, as you can see in the table below, then we carried out a spatial distribution by class. Our objective was to visualize the different classes of entities and how they are located in the environment, and realize that at the extreme end there is a point X, whereby it had a lot of class entities on that side distributed there at one point, and with the changing y coordinate. So this slide basically talks about the label distribution, and our objective was to understand the distribution of the secondary labels and categories, and we used a bar graph, and we were able to understand how the different labels are distributed and we plotted a graph of label against count, and realized that label 0 had a high count than other labels. This can lead to a class imbalance in case we use this, because you can see the label is high, is the majority, while the others are minorities. It can lead to a bias in our model training, and how to solve it, you can either use oversampling or other types of solutions. So we did we did entity type frequency, where we plotted bar plot, which is horizontal, and this was to identify the most common types of entities present and realize that pedestrians were the most type of entities present. So they had the highest count, then bikes, then trucks, then buses, then vehicles, then motorcycles, and then public transport. Then continuing here, we have the correlation matrix and the feature correlation analysis matrix, and these are the key findings. We found out the different values, correlations, how they are defined there, as you can see, like that. Then proceeding to our explainable AI results and discussions, we did some data cleaning. We are able to replace or impute all the values of acceleration with the mean in order to reserve our data set and prevent any data losses, because we needed it for better learning of our model. And we split the data into a 70% training, a 15% validation, and testing was also 15%. Then the results from the STGCN and the GNN are combined both in training, validation, and testing using classification matrices. You can see they are there. Then we also have the other model we use. These are the results for for it. We use the regression matrices, and you can see that according to these other models, their performance, the first model performed better, and that's why we decided to choose it for deployment. We chose the spatial temporal graph convolution network as our primary model and the graph neural network for the support model, and we assembled them to give us the results. So we chose this because this model can be able to models both spatial temporal dynamics, temporal convolutions, and graph convolutions, and it matches the problem structure, the facility nodes connected by a campus pathways, and how flows evolve over time. Then it was extended by the GNN for spatial interpolation as an ensemble for robustness. That is the architecture, the data input, how it's going to be in the APIs we use, the API layer, the front end, so on and so forth. So that's how our interface looks like, and for the demo. And then here we have two interfaces. We have the user experience, whereby here the user is able to see heat maps and also predictions of crowds, and then basically the admin can add different facilities and remove some. Then we have the IP assets, which are our data set, the system architecture, privacy and security mechanisms. Then the limitations and also the suggested the solutions to these limitations, as you can see. Then we also conclusion, we're able to implement this end-to-end pipeline, and also integrate the practical exposure to penalty to reduce overcrowding, and so on and so forth. So these are our future works. We will integrate the campus Wi-Fi logs and event schedules to feeds to ensure rich features, add pathways, events, and students cluster nodes and relational edges. As you can see, prototype federated learning, and embedding anonymization to conduct privacy threat modeling. Then also collect some small external data sets for our research domain adaptations. So those are our references, and these are our acknowledgements. We'd like to acknowledge the Department of Networks courses, in which my course belongs, software engineering, for providing the academic framework and resources for the project, and also special thanks goes to our supervisor, Dr. Galuango Marvin, for his valuable guidance, support, and insights and feedback throughout the project. Thank you very much.